This video, I'm going to talk a little bit about how dynamic effects pop up in measurements, and we're going to talk primarily about mechanical type sensors, mass spring damper configurations, but really this holds for all types of sensors that have those kinds of dynamics. And first and second order systems, like you've studied in other courses in engineering, are very common, and it turns out if you just understand those, it really takes you a long way. So it's worthwhile really solidifying your understanding of those types of systems. Let's start off just by thinking about an ideal measurement. So when you're trying to sense any kind of quantity, let's just conceptually say that that's some measurable quantity X. The best case scenario, right, is if you had a sensor where you could measure Y, and Y might be like a voltage. And so if you had a constant K, right, that's the best case scenario. This is just some constant. The K has units of whatever that quantity is per unit voltage. And in the lab, you've probably had some experience with measuring this quantity. It's a static type relationship then, and it's an algebraic relation. In this case, it's linear. We might call that a zero order dynamic system, right? There's no dynamics, it's just a constant. And it relates the output to the input. Best case scenario. And in fact, that's why, for a lot of sensors, they will just report that quantity, the sensitivity, even though inherently the system has dynamics. And we're going to talk a little bit more about that. That's the quantity, that's how you want the sensor to be used in a region of operation where you always have this constant relationship. It's linear and constant. Okay. Now, since most sensors are physical systems, they'll always have dynamic effects, and so that ideal relation does fail. And so it's good to understand under what conditions it won't work, and when dynamics are significant and how to avoid them. So that's why we study dynamic response, so that we can understand not only how to use them, but also how to design them. So before we get into that discussion of dynamic effects in measurements, let's first talk about really simple case of let's say I have our mass spring damper system. In the case of a beam sensor, so let's say we might study in the lab, we just have a beam, and in one case, let's say we have a fixed base and we are applying a constant force at the tip. Okay, so this is the strain gauge beam sensor, so we might have some strain gauges here, right? And let's think about the case where you just apply a constant force at the tip. So you apply a constant force, this guy's going to deflect, right? Some amount X. Ideally, if we model this with some ideal spring, we maybe estimate K. So we understand the relationship between these, maybe is linear. And so physically we understand the system. Nice kind of configuration to have. The conditions are simple. We have basically a scale where we can measure force or weight, and that's a nice simple case. So that's the like a fixed base system. Even if we had like some effective mass here, right? So that's why I'm now going to refer back to now a mass spring system. This is our fixed base configuration. Remember, that's the one that we modeled. And maybe there's some damping in there where it was fixed. There's some mass, and now we're putting some force on here. Apply a fixed force, even though there's mass. If it's a constant force, then there's no dynamics, right? It's just a constant. So this all still, fits. So let's think about now the base excited case. Now it's the same kind of configuration, except now, right, I am moving the base. But let's talk about moving the base. In this case, let's look at acceleration as an input here. Let's go ahead and write IA. So if we had a beam also, now we're moving this base. So I'm going to just show this as a moving base. Now I've got maybe an ideal spring, and I've got a mass here, and there's maybe some stiffness here. And if I'm going to move this base with some constant acceleration, what would you expect to be sort of a measurable quantity? If I had a strain gauge configuration here, I was measuring the voltage output from those strain gauges. If I move this with a constant acceleration, right, what you're going to do is, right, this mass is going to be moving also at constant acceleration. So you're going to feel, right, a downward force here. It's going to look a lot like this system. So it's going to deflect, and the output's going to be a constant voltage, right? And that deflection induces the strain, which causes a voltage output from the strain gauge instrumentation, right? So this force here is an inertial force, right? That's the mass times the same acceleration that you're trying to measure here. Okay. So those are for kind of static or constant inputs. What we, of course, sometimes have to measure are dynamic inputs. So I wanted to discuss these simple cases as a precursor. Think about this case, the base excited. If there was no motion at the base, well, then that just defaults to the fixed base case, right? Okay, now let's talk about the case of harmonic inputs. Why do we care about harmonic inputs? And what I mean by harmonic is single frequency. So here's a case. Let's talk about the seismic sensor. Remember, this is a base excited system, and I'm going to be moving the base with some motion y of t that I want to measure. And I'm going to think about sinusoidal or harmonic input, and that means, I have a single frequency, omega, as a forcing frequency, right? Omega. Distinguish that, of course, from the natural frequency, which is a property of the system, right, that we've talked about before. Think about also, if I have motion y of t, remember these are related. Very simply, the three different displacement, velocity, acceleration. If I know the amplitude of the input, which actually I don't know, but that might be something I'm trying to measure, but we know that amplitude, velocity, and acceleration amplitudes are related, right, through the forcing frequency, through these simple relationships that we know through these derivatives. The forcing frequency omega in radians per second is also related to the forcing frequency in hertz, which is also related to the period of the forced oscillation. Remember, distinguish this from the unforced response of the system, as you might have seen when we talked about the response of a basic mass spring damper system, or as you've seen in 344. These are now forcing periods, frequencies. Okay. Now, I'm not going to go and derive in detail the model for this system, but one of the first steps you do is, in a basic vibration model this way, is you identify that the sensor output here, what you're measuring is the deflection between the mass and the case, which the case is what's moving, right? So, and that difference, right, this is related to what we might call the sensor output, because we're assuming that whatever is between the mass and the case, we're modeling it with a stiffness K, a spring K rather, a spring with stiffness K. What's important is that deflection, and we're going to call that Z. It's the difference in the motion between the motion of the mass and the case. Okay. So with all those basic relationships understood, let's now look at how we would go about finding the response Z given that forcing input. Remember, in a sensor, the sensor will pick up this deflection, and then what we're hoping to do is be able to infer what the actual motion is, right? That's what's important in a sensing application. Okay, so now let's put this into our base excited excitation model. If you like, we model this through just basic Newton's law. There's, if you took your mass, did a free body diagram, you'd have your spring and damper, and so on. So you'd have your stiffness, your force from your stiffness and from your damping, and that'd be your mass. And so you'd say that the rate of change of momentum, or mx double dot is the net forces. Note I'm leaving out gravitational force, which could be in here, but in general we'll just leave it out. And then we have the spring force and a damping force. And note that those are functions of the differences in the motion between the input and the motion of the mass. I'll let you go through this, but at the end of the day, what you find is you've got a second order equation here in terms of the parameter, I'm sorry, not the parameter, but the variable z, which is, remember, that deflection of the spring or your sensing element. And on the right hand side you have, what is this? This is a force, right? And it's the mass, this actual seismic mass, times the acceleration of the input. So this is sort of an inertial force, isn't it? It's the force due to accelerating the seismic mass with the ground acceleration, right? You can then rewrite that in terms of the mass, the forcing frequency, and the amplitude of the ground motion, y times sine omega t. There's solutions then for the steady state of harmonic input. Is simply z of t is then some amplitude z times sine, and then remember there's a phase in there that's introduced, and this is the basic solution in terms of mass, spring, mass, stiffness, and damping. And remember, omega is the forcing frequency, not the natural frequency. So this is your basic solution. And here's how the amplitude of the input comes into play. All right, so this shows you how the spring would deflect, the peak deflection would be related to the amplitude of the input for a sinusoidal input. And all you'd need to know then are the mass, stiffness, and damping, as well as the forcing frequency. And you could find out what amplitude you have in the oscillation of the mass. But again, that may or may not be, if you're doing vibration analysis, that's something that you would do to find out how much that mass is moving. We also want to use this in different ways, so we're going to rewrite these equations and think about this a little bit more. So I'll talk about two different cases. In the first one, let's call that the seismometer case. A seismometer, I'm going to show you, is a device that can detect the displacement of the ground input, and I'll show you how that works. So take the original equation and rewrite it so that we introduce the parameters that I hope you're familiar with by now, which is the damping ratio and the natural frequency. Basically, I've divided by the mass, right? And now on the right hand side here, note that I've got the forcing frequency is in here squared, and then y of t is the input of the base. So you can see that I've got this term right here. If you think about it, this is in terms of units, that's an acceleration. So this is also an acceleration. Those units have to match. Well, and that's an acceleration. Okay. But in fact, here's the displacement input. So because this is a Newton's law equation, so it does have force. It's apparently a force, but I've divided through by mass, so it's an acceleration equation now. But the input of the ground is the input for this equation on the right hand side. Now, if I take my amplitude function, which I've shown on a previous slide, and I divide by y, I'm going to define this function here, this amplitude function. Okay. In 344, your lecture, you might refer to these kinds of relationships as sometimes in a systems class you might call those Bode plots, but Bode plots are just amplitude and phase functions, right? They're basically these solutions for dynamic systems. So the amplitude function is the z divided by the y. All I've done, remember from the previous slide, is move y to the right hand side. And I've also non-dimensionalized this in some respects. I've defined and put in my definition of my natural frequency, which, remember, natural frequency for this system is k over m. So note that in order to understand the amplitude ratio here, output over input, all you need to know is the natural frequency, undamped natural frequency. Remember, there's differences, and I'll show you that in a second, from the damped natural frequency. And then here's the damping ratio also, which is what is zeta is b over 2 km. Okay. So what this says is all I need to know in order to estimate how the amplitude varies over frequency, remember it's a function of frequency, is to identify these parameters. And also the phase function is important. Okay. Now, what I'm trying to show here now are plots of these functions. Let's just talk about the amplitude function as a function of this ratio omega over omega n, and that's what's here. Okay. I understand these plots take a little while for people to kind of absorb, so I'll just talk about it briefly. If you understand this, you can move forward more quickly. Oh, these little dots moved a little bit. I really wanted to show you how there's the peaks of these graphs as damping changes. And note this graph here, these different graphs is for different values of the damping ratio. And note how the damping, as the damping decreases, the peak goes up, but also at the location of the peak is different, right? By the way, that where that peak occurs is called the resonant natural frequency. Note this is where the natural frequency occurs. This is omega over omega n equal to 1. So that's when omega, the forcing, that's when omega is equal to omega n is right here. So the peak of the response is not necessarily at the natural frequency. It's actually at what we call the resonant. But sometimes you can see as the damping gets smaller, it comes closer and closer to the natural frequency. If you have an undamped system, it's exactly at omega sub n. Okay, but generally we approximate it at close to omega n, right? This is where we say all the dynamics are happening here. I'm plotting this case because this is the ratio of the deflection of that sensor element, the spring, to the deflection of the ground. And I want to emphasize that this function is for a seismometer, which is a displacement input. And note that as the frequency gets very large compared to 1, you start getting these flat line out here. And this is important because this is where, remember we're talking about a nice, perfect, ideal measurement. If I can force this system for this situation at very high frequencies compared to the natural frequency, then I get a near constant relationship between z and y. In other words, it doesn't depend anymore on all of this stuff over here, right? And actually what's happening is, imagine you had this mass hanging here and you basic side, and you can do this little experiment. Get a mass, get a rubber band, and just force this guy really fast. What starts happening is this mass basically stops moving, but the spring is still deflecting. This is what the sensor is measuring. You're getting an output from that, and that output will give you a relationship that is proportional to the displacement of that element. That's how seismometers work. So generally seismometers have large masses, large seismic masses that barely move while the ground vibrates, and you can pick up that relative motion and build a displacement type measurement. Okay, and the region where that happens is, again, for omega large compared to omega n. You want to operate at so this frequency for seismometers tends to go very, very small. The natural frequency for sensors that you want to measure, to say ground motion, is very, very small. So I'll move on from this because we want to talk about accelerometers. I wanted to put this slide in here just so that you remember that undamped natural frequency is different from damped natural frequency, right? Because damped natural frequency depends on zeta. And then on those frequency plots that I was just showing, there's another frequency that we defined, which is based on where the peak might occur, and that where that peak actually occurs is the resonant frequency, and that could be different from the natural frequency. As you can see, it depends on how much damping you have. You can see if zeta goes very, very small, then those are approximately equal, but they are different. Okay, now so let's talk now about the second case, and this is accelerometer model. Sorry, same system, but I'm just writing it differently, right? The y double dot, I'm going to just say, well, before I defined that and I focused on the input amplitude, now I want to focus on this as an input being the acceleration, and I want to get a relationship between the amplitude of the deflection of the spring, right, and the amplitude of the acceleration, because I want to measure acceleration. Okay, so when I get the solution in this case, now I can just rewrite the amplitude function as a ratio of, again, z, which is, remember, the amplitude of the deflection of the spring in the mass spring damper system, to the amplitude of the acceleration of the ground. And now I get a different amplitude function. The big thing to notice here is that compared to the seismometers, that there's no omega, the forcing frequency is not in the numerator here. It's only in the denominator, which is the same for both systems. So in other words, this is a constant on top. It doesn't depend on that omega. And that's important. When I plot that, I get a function that's slightly different. I don't know if you'll remember, but for the seismometer, the graph, was z over y. And when I plotted that versus omega over omega n, it started off like this, and it went this way, and then we liked to operate up here. I flip that over now when I start looking at acceleration down here, right? Now I have acceleration here. This is z over a here. And note, I get a nice flat spot here. And so when omega is very small compared to the natural frequency, remember the natural frequency is somewhere around here, I get what I call my bandwidth, which is where I want to operate my accelerometer. I get hopefully a nice flat region. And that ratio then between z and a is a constant. And remember, that means that I can if I have some constant k times peak acceleration, that's what I call my sensitivity. Right? It's going to have units of displacement per unit acceleration, and if I can then show that, and I'll talk about this shortly, that this displacement can be measured with some sensing element, then I have a way of measuring acceleration by measuring the deflection. I'll talk about that shortly, but you can see the difference between an accelerometer and a seismometer is, again, the accelerometer, you want to use it when the frequencies are very small compared to the natural frequency of the device, whereas a seismometer up here, you want to operate it for frequencies that are very high compared to the natural frequency. Okay? I'm not talking about in this video what a geophone is, but a geophone that's also used a lot in measuring ground motion. Actually, in that case, you would get a z over what? Velocity. Okay, and we're not going to talk about geophones here, but those are used a lot in seismic measurements as well, ground motion detection. So if we can model our beam mass system, remember this is the base beam, maybe some mass here, and we have strain gauges. If we can model this as a mass spring damper system, and we can use strain gauges here to basically detect the relative motion between the base motion and the seismic mass motion, then we basically have an accelerometer from this beam mass system. Is it perfect? Well, that's something that you see in the lab, but that same transfer function relationship that gives you the amplitude and phase functions will be the same as the one we just looked at, right? So note that all you need to know what's the relative motion between the mass and the base is this function, and all you need to know basically is the natural frequency. This numerator, the numerator and the denominator just tells you, if you look at, again, plot this versus the forcing frequency that you're actually vibrating the base here at relative to the natural frequency, and let's say that that's 1 here, where those are equal. as long as I'm operating down here, then this value here is a constant, and it's just basically this value here, right? It's 1 over omega n squared, isn't it? If I start getting close to omega equal to omega n, right, you start hitting a resonance, and so you expect this guy, depending on damping, you get different. So you want to stay away from this area here, right? And you want to operate, and this is repeatedly we'll call the bandwidth. This is the nice region to operate. Okay. And as I'm saying down here, this function tells us how much the beam tip would deflect for a given level of base motion acceleration relative to the base, right? And so if you think about this being a strain gauge system, that strain gauge is going to respond to that difference in deflection, and so you get an output voltage that's proportional to that deflection. And that's what you will look at in lab. Just another note to make sure that you think about sensitivity on accelerometers. That amplitude function relates displacement to input acceleration for an accelerometer, and it has specific units, so keep in mind that sensitivity will have units depending on what you're looking at. In this case, the direct transfer function is deflection, say, versus acceleration, but if you have a sensor, you want to have, voltage to acceleration. So the units sometimes for accelerometers will be reported either as some voltage per acceleration, per g, or per meter per second squared, depending on how the manufacturer decides to report that. And then the bandwidth would also be reported, and I'll show you some examples here in the following slides. So here's an example of a accelerometer made by Analog Devices, and in this case, this is an accelerometer that uses capacitive plates to measure the deflection between a seismic mass and the base of the accelerometer. And look at the I've put a green shadow here. The actual amplitude plot actually is flat here. This is your bandwidth, and then it really tapers off here. And note that there's a peak over here, right? The actual natural frequency for this guy is somewhere in this region, around 1,000, but it's highly damped, so there's no resonant peak here. This peak is probably due to some other dynamics in the actual accelerometer, some other structural vibration in the case, or so on. So the actual resonance is actually here, and so when they report the bandwidth on this device, they would report that it's only useful in this region up to about 100 hertz, because you don't want to be operating in this region, because you know what this constant is, right? That's the Z over A, if you like. Here's another example of a device made by a company that used to be called Sensotec. Now it's actually owned by Honeywell, and this is a device that actually uses strain gauge like elements in a package. And again, here's a nice flat, oops, I actually colored this wrong. This green shadow should be, so the bandwidth is actually, I moved this image and didn't move the green part. So this is actually the bandwidth, right? So disregard that green there. So the sensitivity is this graph here, and you can see it tapers off over here. Here, that's about 100 hertz. It's about 200. So the bandwidth for this guy is probably out to about 200 hertz. Okay, and it's flat in this region. And note they actually have the specific number here. The sensitivity is reported as 10 millivolts per G, and at DC means at zero frequency. This is actually about a frequency of 50. So you would expect it to be flat all the way down to about zero. DC is 0 hertz basically. All right, so nice and flat up to about 200 hertz. No resonant peak here. Again, it's a nice highly damped device, so there's not going to be a lot of ringing in it if you excite it. Speaking of ringing, here's another accelerometer. This one is actually a piezoelectric accelerometer made by a company called B&K, and here I've again marked the bandwidth. This one's out to about 5,000. This is a device that, and note this is 200 hertz is the lower, so actually piezoelectric elements don't go, on the lower side they start tapering off too, so there's only a region in between the low frequency and the high frequency that's useful. they have a roll off at low frequencies also. Roll off, I mean that you can expect that amplitude function would actually go down on this side, and that's just because of how the piezo element works, and the measurement of the charge on those elements works. But the thing I wanted to show here is that look at this resonant peak on this case. It's very lightly damped. So if you start exciting this guy at really high frequencies, you're going to start seeing some ringing from that natural resonance. Okay, so again, this is why you want to operate in that flat region. So showing you a few examples there of different types of sensitivity functions and how we define bandwidth for different types of accelerometers. The last one I wanted to show you was the one called the crossbow accelerometer, which is the type that we use in lab, and this is actually also a capacitive based accelerometer, but sometimes I want to show you an example of the spec sheets. You'll see that this is the accelerometer that we use in our lab, but let me blow this up a little bit so you can see better the specs that you'll see for these types of devices. Note here's the input range. You can measure accelerations out to plus or minus 4 G's, right? And there's sensitivities right here, millivolts per G. This has 500 millivolts per G, and so on. Here's the bandwidth, DC to 100 Hertz, right? So DC means it goes down to 0. So we can actually measure, when you see an accelerometer that has DC, it means you can measures constant acceleration also. What does that mean? It means that it can basically see G, right? It'll respond to the Earth's constant acceleration, for example. Okay, and you'll see changes in voltage when you excite it with the constant acceleration from Earth's gravitational field.